I thought you there
Oh, I wish I could have gotten that done in 2 hours. I'm still figuring out how to get turbine efficiency.
Do you not just do what we did earlier?
I can't.
You can't get the theoretical efficiency?
No, because it's super critical carbon dioxide. You can't use PBV, you can't use ideal gas. I don't have a relationship to use polytropic with the process.
Like, what is the theoretical?
No, because there's heat output.
Okay, then you probably have all your sleep last week.
All right, cool. Welcome back. We're in this is the last kind of assigned module of the stuff that I say, like, yes, this is important. You should figure out how to apply this. Mute myself. There we go. That's better. I can only listen to one Professor Cooper at a time. Maybe the symphony is good for other people, but yeah. So that's where we're at today. So this is like energy and momentum methods. It's same idea that we've been working with, of like identify what forces there are, what are the constraints on motion. Just now we'll look at two other ways of talking about like what kind of equations we can use. So we can jump like right in to, I guess I should have opened this up first. Chapter 4, coming down all the way into the problems. For I think it was it 4-2, right? Yeah, that's where we're starting. I'm like, what? I was lost for a second. And then we go to 4-6. All right, deep space. Our spaceship is 10,000 kilograms. The thruster is creating a 100 newtons of constant force, constant thrust. If the spaceship is moving 50 meters per second and the thruster is anti-aligned with its velocity, how long should we fire to bring the spaceship to rest before absolute disaster in deep space? Sometimes you have to add, they leave things out of the textbook sometimes. But, so what do we think?
I'm thinking we should draw a picture before we draw through by diagram.
Picture? Yeah.
Yeah. Could you?
Yeah.
Yeah, I want to draw some of the numbers, make it one. Yes.
Right. There we go. But then we have this like little forward thruster. Firing off anti-thrust. Anti-thrust laws. So we're moving in one direction, or it could be that we're like even traveling backwards. Like, if you ever played the asteroids game, like as soon as you start moving, you can, once you're moving, you can spin the spaceship around and then kind of push back to where you came from. But we'll just, it's all right. Yeah, and it's actually one thing that surprises me a lot about like orbital mechanics things is that the moment of inertia of the spaceship is just assumed as a point mass. Like, but they're pretty big, like 10 to the 4 kilograms. That's a lot of mass, so it's hard to get that into like one point. But usually the motion takes so long compared to how long it takes to rotate it that it's fine to say, like, all right, if we need to rotate, we'll have plenty of time before we need to rotate and then thrust. So it's just a point mass with thrust going in any direction that you want it to for a model, for like our physical model. All right, so what do you want to do? I want to know what you want to do here, because you have tools, and power, science. You want to sum the forces? What do you think of that? And then do what? Sum the forces. Yeah. What will that tell you? Something. Restriction force. Okay. Okay.
I'm joking. What if we were in shallow space? And you can asteroids and shit. Friction problems. Yeah. Huh? Yeah. This guy gets it. John Rowland among those beach.
Yeah, so the thruster is like, it's almost always like external force.
So yeah?
It's creating that much force on this object.
Yeah, there's kinetic diagram.
Yeah, you know, how much force does that tell you? Does that tell you
I mean, since you're slowing down, you're accelerating to the left, so your kinetic diagram is the same as the by the diagram.
Yeah.
Is kinetic diagram?
Yeah, but you're accelerating, you're slowing down, so you're accelerating backwards.
Oh, is kinetic diagram like acceleration?
Yeah.
What about velocity?
No, it's acceleration. It's slowing down.
But the thrust is constant.
I know, I agree. Is it how it's moving or how it's accelerating? Oh, this guy. Chat, type 1 if you think I'm making it wrong. Remember that one time somebody was typing?
Oh, really? Yeah.
No, but
Yeah. But here we have
You don't say. The chapter like momentum.
I did it on my mind.
50 kilograms.
For this class?
It's like the opposite.
I don't do the reasons either.
Yeah.
I don't do the reasons.
I like physics too.
Yeah. If you're looking at it,
The book is pretty intense. Yeah.
The book gives us our exam problems.
Yeah, I was looking through the book out. I was like, oh, sweet.
What do we think? What was the starting point here so far?
Free body and kinetic diagram.
Free body kinetic? Okay. What does our free body diagram look like?
We got just one force, force of the thruster.
Okay. And that's it? Yeah. Yeah, I mean, deep space, like the reason you assume deep space is that no gravity, definitely no drag, no friction, right? Like you're just, the only thing affecting your motion is whatever you apply to it. What does our kinetic diagram look like?
Is kinetic diagram acceleration or velocity?
It's all, so kinetic diagram is always showing like MA.
Oh, okay.
Yeah. To the left?
Because you're slowing down.
Yeah, you can say to the left. But then really what you're saying is that you're like reversing your X and Y act, like creating a mirror. Because wherever you say MA is pointing, that's your positive X axis, or positive kind of direction axis. Yeah.
So if we were to do standard, here would go. Right?
Yeah, I only do. I always do that to make sure that my signs are correct, because I'm moving in a positive if I say that I'm moving in a positive 50 and I'm trying to get to 0, I need a negative acceleration, right? So positive 50, subtract something, then at some point I get to 0. If I keep applying thrust, now I'm going backwards, so now I go back to where, yeah. Again, you can.
Should it more so describe like the reference frame as opposed to the actual motion of the wheel?
Kinetic diagram is always just describing like what is acceleration in your reference frame. It's not necessarily like what is the correct direction for acceleration. And if you always maintain that system, that you're always saying this is what a positive acceleration is, then positive and negative is always describing going forward or going backwards. And it's a nice way to like maintain and create like your equations of motion and have some consistency in this crazy inconsistent world. Okay, seems like this could work. So what would you do? So what do we do next? We have free body diagram. Yeah.
We're going to be like momentum and impulse.
Ooh, momentum impulse. Why is that?
Because you've got mass and velocity, so it's got momentum and impulse.
Okay.
Force times time, so it's
Yeah.
got the force.
Yeah. What do people think about that? Momentum is force times time? Yeah.
I did it in kinematics where.
Or kinematics. Okay, kinematics. Why does kinematic equation, why do those work?
Well, because it's a constant press is a constant force.
Yeah. So here, because this is constant, so Ft equals, or I guess like a negative Ft equals ma. Why don't we just plug in the 100? Since it's a constant 100 newtons, A is constant. So we can plug that right into kinematic equations. So we know A, now we know how far it's going to move. We can figure out how much time it takes for that velocity to go to 0, right? All that kind of information. Yeah, something like this. I guess really this would be like A delta T. So in this case, we're kind of going through like 2 or 3 steps, right? Like figure out free body diagram, kinetic diagram, find A. Is it constant? Okay, it's constant. Now integrate the equation, which we already have like the kinematic equation integration there. But another way is thinking about impulse and momentum in the same way that we drew like free body diagram, kinetic diagram. We can look at changes in momentum and set that equal to whatever caused that change. So whether it's an impulse or an impact or just a force acting over time. So what this looks like is like initially we have NV0 moving to the right. So I'm drawing like what does my momentum look like? And I'm going to add to that like an FDT, which is my impulse. It could also be another way that we can describe this is just like some average force over a delta time. So even if we didn't know like what the force was, here we're told it's a constant 100 newtons, but maybe it's just sort of like, all right, we know we need to apply thrust. At first it's going to be real low, and then it's going to ramp up and then come down. We could figure out what's the average force we needed, and it's still the same equation. And all that is going to be equal to that MV final, which is 0. So here there's no, I'm not plugging in like kinematic equations, I'm not solving for acceleration. I'm just saying that 10 to the 4 kilograms times that, how fast are we going? 50 meters per second minus 100 newtons times delta t equals 0. So anytime you need like force and time or average force over time, impulse momentum gets you right there without any other equations. I mean, you have to know where the forces are applied and how they're being applied, but you can directly add them up and figure it out that way.
What's like the difference between impulse momentum?
What's the difference between impulse momentum? So this one is momentum over here. This is impulse. And this is like, I guess, initial momentum plus an impulse is my final momentum.
So when you integrate impulse with respect to time, you get momentum?
If you integrate force over time, you get impulse. So momentum is always force times time. Like, so 10 newtons applied for 10 seconds is 100 newton seconds, which is 100 kilogram meters per second. Like, it'll create that much motion. And a lot of times this is more useful, especially for things like impacts or explosions. This is a more useful way than saying like, okay, I had infinite acceleration for a really short period of time. It's better to just say like, all right, I had 10 newton seconds of impulse applied. It's also great for something like a rocket where I know how fast my propellant is going to leave, and now I can like measure out, like, all right, let me release 50 kilograms of propellant, and that'll slow me down because I know how fast it'll leave. So yeah, rocket, a lot of it is like, if you look at rockets, how propulsion is measured, it's like specific impulse. Like, what is the impulse that this fuel can create in space, which is over here, our impulse. No, anyway, yeah. So what do we get? How long do we need to fire the thruster? And you can do it either way. Either set up what is acceleration and solve for when is v equals 0, or plug it right into impulse momentum. 5,000. How does that sound? It's a big ship with a small force.
5,000 seconds.
Yeah.
So like 2 hours.
3,600. It's a little less than 2 hours, right? 3,600 is 1 hour. 2 hours is like 7,200. Like hour or something, hour and a half. Cool. I think next one is 4-6.
I just look at your calculator.
1.3.
Okay, yeah, you get this.
All right, this one, I want to give us like a roadmap of what we're doing, because we're getting a lot of work. We're going to get like a lot of check marks along the way of like all this stuff that we're doing. So we have one way you can think about this is almost like, remember pendulum is basically like a mass on a spring, like for a linear pendulum. This could be like a table with like this pendulum that's sort of like moving around in a circle, like swinging around this way, or like a mass on a spring. It's also same kind of motion, but it's moving around in some kind of like ellipse is the main kind of motion. So first off, we're going to have like 2 different frames, one where the table's moving, like, so this thing is moving in an ellipse and we're moving the table. And then the other one is just thinking about like if the table is our fixed reference frame. And then we're gonna show what is the angular momentum in both frames, both the moving one and the non-moving one. And so we're doing that so that, and I'm saying that because there's a couple of like setup parts of like define position, define velocity. So angular momentum is based on position velocity, and it depends on what your reference frame is. So we're going to have 2 different reference frames and compare the 2. So here's like using coordinates of your choice, create what is RP/O prime. And then this thing, again, it's like moving in an ellipse around this O prime. So the first step is just trying to figure out, how do we describe this? And it's not, we're not trying to like come up with numbers for this. We're just trying to say, what's the bare minimum of things that we need to know to describe its position and its velocity. So how many degrees of freedom does it have? 1, maybe 1, maybe 2, maybe 3.
It's like X, Y, and then Z.
Not rotating.
Like spinning?
No, it's rotating.
Rotating like in a plane.
Yeah, rotating in the XY plane, and it's bouncing, so that's 2.
That's 2.
Not rush 2.
2.
Oh, it's 2.
How many so we're considering it a point mass, right?
You should have the radial direction and the theta direction.
Yep, so we could think of it as like we have an R and we have a theta. And that's all you really need for point mass. It's like some way. We do have like this constraint that the table has to move at a certain speed, like v0, but that's describing how the spring is attached. It's not saying that the thing has to move. It's like the spring has to move and it's going to drag it along with it. Yeah, so 2 degrees of freedom.
It's like for scales. It's gonna be on a blueprint.
So we need 2 coordinates. We could use r and theta. We could use x and y. We could do something weird like y and theta if you really feel like punishing yourselves. But yeah, what are the 2 coordinates? And then once you have those, what does it take to describe position velocity? This one, it's not a lot, like we're not doing math right now, we're just writing out some kind of definition. What do you think? Not sure. Okay. Yeah.
Visualize this.
Yeah. R and theta? Okay. So what would position look like if we say that R and theta is our 2 coordinates?
I don't even know what the question's
Like
asking.
it's okay, but we can just say like, okay, there is an R. We don't need to know like what it is because we know it's going to be changing. If I say my position is going to be like R in a certain direction, that would be like, yeah. 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 Yep.
Beyond two.
Like one way you can always go back to like Cartesian coordinates instead of because at rest length I know I have an XY location.
It's at the rest length, then
R is
the length R
plus
is
Y. All the numbers are
So the
what's constant. Even though these things are changing. No.
so like what would you
I hear you. Should be able to figure out.
maybe she's watching.
I was gonna say, hey,
Is there one?
What do we think? It's a weird question.
Can you rephrase it again?
Yoda style coordinates using the choice no, sorry, that doesn't help. So here, really, like for this part A, the problem itself doesn't really matter. Like if you're just choosing coordinates and choosing how to describe the position of an object, of just a point, then I mean there are ways that'll save you some time and ways that'll like increase how much math you do, but you can always go back to like, hey, this thing's moving in 2 dimensions, like I don't care about its z-axis, so it has an xy position. So position is x along that B1 plus y along that B2. And that's a totally valid way to say, that's my position. It's going to add some work down the line, because now we're going to have to do a lot more trig and maybe some trig identities. Because we're taking we're taking a square coordinate system, jamming it into this rotating coordinate system. So another way is we could say, like, all right, instead of B1 and B2, I'm going to say that it's some radius along that ER direction. Let's use like blue.
Are you just transferring the frame?
Yeah, just creating a new reference frame that is ER. And ER is always like some theta off of the x-axis.
What's like the point of like putting those two frames next to each other? Because they go in the same direction. I guess I just don't understand why there's E and B.
So E is a fixed like point, and then that O, so we have like O over here, which is not moving, and O prime is moving away from O in a constant speed. So it's like this thing is all set up on a table, but the table is rolling away. But it's rolling at a constant speed. Yeah, again, there's a lot that we're going through. It's kind of fun to go through it together. At least I like this stuff. So if that's our position, what is velocity? What does that look like?
Could you take the derivative?
Yeah.
R dot.
Yeah. R dot. So we could say, oh, it's just x dot plus y dot along those two directions. And that's exactly the same as r dot ER. Is that all we need for?
Wait, why?
Isn't there like theta?
Some kind of theta, right?
Yes, it's like spinning circle, so.
Yeah. And again, we can always, like, whenever we say we're using r and theta, it's a polar coordinate system. We can always look up what is velocity in a polar coordinate system. And it's always going to be a function of r and theta. But yeah, so look it up. Imagine I just looked it up. I found it, went through the textbook. So I can say that it's r dot along that radial direction, and then r theta dot in that transverse direction. So that one's describing like the direction of opening the angle.
What did that say?
L. Maybe.
Which one's L?
Oh, is that E?
Oh, it's E.
Oh, E, yeah. Yeah, there's ER, E theta, which are the relative to O prime. That's it. Like if you're being asked to define like what is position, like this thing, R and theta, X and Y, they're all functions of time. They're all related to each other. We're not trying to solve for them. We're trying to figure out what's constant even when these things are changing, which again, it's kind of a weird thing to do. Usually as engineers, we love numbers, but the numbers will add up to constant value. All right, so next, now we're here. Oh. So we just defined RPO prime and VPO prime. Let me draw this out again.
Yeah.
So every second we're going to be V0 further away, like if 10 meters per second, every second we're 10 meters further from O. And we just defined that relative R, so in that moving frame, what is the global RPO? How do we define that one? And remember, we said it's 2 degrees of freedom, so we should be able to define it just as like a function of r, theta, or x and y, however you want to do it, but somehow just your 2 chosen coordinates and time. You can use time as part of it because time is always like whatever value you want it to be, or a whole range of values. Y is the same. Yeah. Yeah.
Well, we're working in radio coordinates, right?
Yeah.
So it's just that R
I'll get a new theta or create like a new radial. Yeah. Okay.
RPO?
Yeah.
That means where is it?
Yeah.
Are we using tree? Can we use tree? Because then I can just triangles. Because then wouldn't the distance in the x direction just be d equals t plus cosine theta? Cosine plus RPO prime cosine theta? What's
I thought RPO was spinning, yeah. Okay, let me go negative. Which doesn't change what you said.
oh, the cosine would account for that.
Guys, did you pick up your exams?
Yeah, we are.
They're missing one exam.
I'm not sure. They're missing one?
Mike, are they missing yours?
They still have one?
See if you grab someone else's midterm 2 by mistake. We're missing one exam.
Are we supposed to give them back?
That means someone tried to get this and didn't even do it.
Yeah.
I didn't try yet. Yeah. I think we're two different. You should give me 100 because obviously you don't even know where the numbers are.
I feel like it just give you a 0 instead.
I know I have one.
Well, it means someone went and did it. That's not how it
And maybe they picked up like 2 exams instead of 1 because they're like,
Yeah.
studying that one.
It's gonna be here. And then it's like, first we go to the 90 days, so like, it's gonna be here.
And I'm like, oh wait, I don't
So when you take it to the I could not.
That's still a good grade.
Alright.
Yeah, it's very good. What is that?
8. Thank you, Shane.
Yeah.
So since what you guys said, I feel like all you can do is the initial plus the cosine of R O prime,
What
which
happened to
we
radio
have,
What happened to radio coordinates?
Yeah, that is using.
Yeah, we have it. We got it from part A in radio coordinates. Yeah, exactly.
As long as they're on keep track. I don't know. What it makes sense.
It's just
add
like tip the tail. If like one vector going this way, another one going that way, but like as you should end up in the same spot.
I got this from here. I don't know what frame this is in. Well, it has to be in the same one actually.
Similar font. Okay.
This frame exists.
We just added.
Just
We
adding.
did v initial times t plus the RPO prime we got from part one. The cosine of that.
Can I do this? Sorry, it'll catch up in a second. Is there any difference between this E1 and B1? Any difference? What happens if you move a unit vector?
Oh, it's the same.
Same unit vector, right? So whether I want to use B1 or E1, like it's all, even though they're moving relative to each other, they're always pointing in the same direction. And a vector is a vector. Like it only describes magnitude direction. Unit vector is only describing direction. So if they're both pointing in the same way, it doesn't matter where they are. It's all. Can I do this though? Like now I have like B and ER. Is that okay?
I don't think you're allowed to do that.
Not allowed to?
You can, but it's suboptimal.
Suboptimal? Okay.
Put them in the right, same coordinate.
You want to put them all in the same frame?
Cosine would go crazy.
Yeah. I mean, here, as far as like just defining what is position, it's okay to mix and match unit vectors. And it's going to save some work. It'll make some extra work, but also save some work because now I'm not like doing a whole bunch of work to begin with to get it all crammed into one coordinate frame. So it's okay, but we just have to remember when we use B1, there is a component of B1 in ER, right? So if we're doing like, so some of it will get added and then another part will get added to a different part. You can mix and match, it's okay. We can, it's our coordinate system, right? We can use it however we want. If you don't like that, you can try it. You can try it either way, but I'm gonna leave it. Just see how it goes. Because now when I take a derivative, what does that one look like? What's the derivative of V0t B1?
With respect to t, it's just V0.
Just V0. And B1 is always pointing to the right, so. And this is what I mean. It saves a little bit of time and stuff like this. And now, this RER, I already figured that out. It was R dot ER plus R theta dot E theta. Now I've got 3 different unit vectors, but as long as I'm keeping track, it's okay. You can mix and match unit vectors. I'm just putting our coordinate systems into our free body diagram. What does the free body diagram look like?
No, this.
You tell me which force, bro.
Provide some of the force. Because you saw my earlier diagram, it's like angled, so the spring is like
Just this one.
not how it's moving.
So we put the thing on a string and then put that on a table and then we push the table. Yep.
Push the table, or push the table. I didn't realize
That's what
the
we just
table
drew in
was
the
being
last
moved.
session. The table is being moved.
Oh, that changed it a lot.
I need more pictures. Who's spinning? Who's on first?
I thought it was spinning like in a circle.
It's watching the power string.
Oh, she's not spinning it.
Yeah, she's been listening to us the whole time. I just said keep doing it.
We're on a wire.
Well, Graves probably wearing a line for free buy. That's everywhere. That's what I was on.
Usually that kinetic diagram.
You're the ones who talk to most people. You also talk the loudest too. Everyone else is quiet. I didn't need a wire when I was on the street.
Chat, who's louder? Me? Guys, it's just the spring. What else is acting? Like, I know it's spinning, but it's just spinning. It's just spinning. I don't know how to take that into account. It's spinning because it is, and the spring pulls it inward.
It is spinning, I thought we did it.
I don't understand what it's.
It was like orbiting.
Do we have like the thing going like this, but then it's on a table and you push the table down the hall? Is that what's going on here?
Yeah, yeah.
Okay.
Or like you're watching it go by on a train. Like
I like
this
that.
system is moving and you're like, whoa. And so there's like your
Okay,
fixed
that-
reference frame of you watching it happen versus like someone on the train that was like, this is cool. Yeah. We were just playing yesterday, we were playing with a slinky. My parents gave my two kids a slinky. Like, oh sweet. And we got it to like go down the stairs because they're in an older house, so you can actually get it to like go from one stair to the next. But anyway, sorry, that one's unrelated, but it was still cool.
I think it's time.
I think you mean the medieval portrait.
Force of the spring going right at O prime. Anything else?
Nope. Force? No, because it's constant.
There's no.
Well, so it's nothing about the velocity is constant.
Gravity.
R is changing, theta is changing, like
If we're assuming constant Z position, we'll just say
Z position is constant. We're saying like that it is on some kind of like table or like one plane of motion. But yeah, that's it. You just have that force of the spring. Nice.
Oh, we're done. What about the
That
other
was it.
It's just sitting there?
Does the free body diagram depend on a reference frame?
It's not.
No? Why not? It's just forces acting, and if the force is there in one reference frame, it's still going to be there in another reference frame. That's a different question if you're changing like what system you're looking at. Like if you said what's the free body diagram on the table plus the spring plus now the spring is an internal force, like that's a separate question. But as far as like what are the forces acting on this particle, however you draw your reference frame, they're still just pointing in the same direction because a vector is a vector. And we can even skip the kinetic diagram because we're using like momentum methods. Save us a little bit. And this one, I mean, it says find angular momentum, but I don't want to go there yet because I want to look at the sum of the moments. because we just went through the work of drawing a free body diagram. So we know where the forces are. We know, and since there's only one force, we already know what the sum of the forces are. What does the moment look like in O prime? So the moment around that moving reference frame.
Force times distance.
Force times distance.
Times the arm.
Yeah,
The
what
arm is
distance?
changing.
Arm is changing. Yep.
Did we say it's a kingsman?
Well, no, but it's on a string.
It's on a spring.
Oscillate. We just use the, we don't really use the expression we used before.
Like a fixed duration.
Okay.
The position of, so it's Fs times R.
Okay.
R. Problem, I don't know.
So you think we could do Fs times R dot product? Or just multiply?
I mean, technically it's dot product, but in statics. we have-
Cross product?
Or maybe it is cross product.
Yeah.
What's dot
We
product?
had, I mean, this was a while ago, but we did a moment, right? Of like, what is a moment and a torque?
Yeah.
We had a moment. Oh, we're out of time? Oh, sorry. All right.
Speaking of moments.
Yeah. So general definition is always, what is your position, like actual vector position, crossed with your force. And this one, we can do, I mean, we're out of time. All right, so
What does the bar mean?
Static problem.
bar means that it's a vector. Instead of just saying like k times r, it's like kr in the er direction, negative kr er. All right, so we'll come back.